ടോപ്പിക് എന്ന് പറയുന്നത് ക്വാണ്ടം മെക്കാനിക്കൽ എൻസംബ്ലെ തിയറി ദ ഡെൻസിറ്റി മെട്രിക്സ് ആണ്. സോ ഒരു ഡെൻസിറ്റി മെട്രിക്സ് എന്താ നമുക്ക് നോക്കാം. സോ ഇറ്റ് ഈസ് ഓൾസോ കോൾഡ് എ ഡെൻസിറ്റി ഓപ്പറേറ്റർ which actually plays the role of a state vectors as they encode all the accessible information about a quantum mechanical system. So it turns out that the pure states described by the state vectors like psi on Hilbert space are actually the idealized descriptions that cannot characterize or sum statistical or incoherent mixtures which we often see in experiments, that is actually in nature. But these subjects are very important for the theory of quantum information and quantum communication, that is the density matrices. So let us look more detail into it. So let us discuss about the general properties of a density matrix. So consider an observable A, where A in the pure state psi with the expectation value given by A of psi is equal to the product of states and A. So by definition, a density matrix for a pure state psi is given by rho, which is equal to the products of psi, that is the pure states. സോ ഇതിന് 4 പ്രോപ്പർട്ടീസ് ആണുള്ളത്. ഒന്ന്, റോ സ്ക്വയർ എന്ന് പറയുന്നത് ഇറ്റ്സ് എ പ്രൊജക്ടർ, ആൻഡ് റോ ഡാഗർ വിച്ച് ഈസ് ഇറ്റ്സ് ഹെർമൈറ്റിസിറ്റി, then trace of rho which is equal to 1, that is actually the normalization, and rho greater than or equal to 0, that is its positivity. Now the properties 1 and 2, that is projector and hermiticity, actually comes from the definition of equation 1, which we just saw the expectation value of A. Now property 3 can be verified by using trace operation for an arbitrary operator D. So trace of D, which is given by the product of n summation n, the products of n and D, where n is actually an arbitrary constant. Now taking the operator D to be the product of two states phi and psi and calculating its trace, we get trace of D as summation n products of n and the two states psi and phi. On rearranging, we get summation n psi products of n and phi, where the products of n or arbitrary constants are actually equal to unity, and trace D ultimately turns out to be the product of the two states phi and psi. So when these two states phi and psi are equal, we get trace of D actually equal to 1. Now property 4 means that, or positivity means that, the eigenvalues of rho are greater than or equal to 0, which can also be expressed as product of phi and the density matrix rho, which we can write where we define rho as the product of two pure states. So we get the product of phi, two states phi psi and phi psi. So it is actually equal to the square of the product of two states phi and psi. So we know that square is always greater than or equal to 0 or greater than 0. So this is an important property because probabilities are always greater or equal to 0. Okay, now let us discuss about pure and mixed state. So consider an ensemble of given objects. Okay, let's begin with pure state. Consider an ensemble of given objects in the states psi of I. Okay, if all objects are in the same state, that is of all objects, if all objects are in the state psi I, then the ensemble is represented by a pure state. So the state is actually characterized by the density matrix of our definition from the equation 1. So with the properties 1 and 4, that is its projection and positivity. So we can combine the property 1 and 3, that is actually the projection and normalization, to prove that trace of rho is always equal to 1. Now let the system in the state psi, which we can expand with respect to our eigen states of an operator A. So we write the state psi to be summation n c n into the product of n, where a to the product of n, a n is given by a n, small a n, where small n actually is the eigenvalues of the operator a. So the expectation value is given by a of psi is equal to sigma n cn square into a n, where cn square is n of n divided by capital N, and cn square is actually the probability to measure the eigenvalue a n, and which is defined by nn by n, where nn is the number of times this eigenvalue has been measured out of ensemble of n objects. And as I have told earlier, this state is actually characterized by the density matrix of our equation 1, where we combine 1 and third property to conclude trace of rho is always equal to 1, that is normalization and its projection. Now next, the mixed states. So here it is contrasting to the pure state. So in this situation, not all of the n systems of the ensemble are in the same state. That is, ni systems are in the state psi I respectively, such that sigma of ni is always equal to n, and the probability pi to find an individual system of the ensemble of this state psi I is given by pi, that is the probability, which is equal to ni by n, where eventually sigma ni is always equal to n. So sigma I pi is always equal to 1. So the density matrices of this mixed state can be written as summation I pi into rho I of pure states, and rho I of pure states is actually the products of the states psi I, and the expectation value is given by a of rho mixed state is equal to trace of rho of mixed state and a. Next, quantum mechanical ensemble. The quantum mechanical ensemble theory. Now consider ensemble of n identical systems where n is always greater than 1. Now this system is always characterized by an Hamiltonian operator h cap, and at time t, physical states of various systems in this ensemble is characterized by a wave function psi ri of t, where ri of t denote the position coordinates. Now let psi k ri of t denote normalized wave functions, where physical state in which kth system of ensemble happens to be at time t, and we can write k is equal to 1 to up to n. Now the time variation of the function psi k of t will be determined by the Schrodinger equation. So from the Schrodinger equation we get h cap psi k of t is equal to ih cross psi dot k of t. And now introducing a set of orthonormal function phi n, we can write the wave function psi k of t as psi k of t is equal to sigma n a k n of t of psi n, where a k n is actually the coefficient. So a k of n, that coefficient, is equal to integral psi n star psi k of t d tau, where psi n star is actually the complex conjugate of psi n, and d tau, which represent the volume element of the coordinate space system. Now actually the physical state of this kth system can be described in terms of this coefficient term a k n of t. Now let us look the time variation of coefficient. So time variations of this coefficient is given by ih cross a k n of t, actually the Schrodinger equation, ih cross a dot k n of t. So by substituting the equation 3 for a kn of t, we get IH cross integral psi n star phi n star phi star n psi of k of t d tau, so which is actually equal to psi n star h cap psi of k psi k of t d tau. That is from the equation 2, equation 1. Now which is equal to integral phi n star h cap a k m of t and phi m. That is actually we are substituting for psi of k of t, so which is equal to integral summation m h m n a k m of t, where we substitute h and m is equal to integral psi star h cap phi m data. These are actually the rearrangements that are introduced in this equation. Now, speaking about the physical significance of the coefficient a k n, it is actually evident from the equation 2. From equation 2 that these are actually the probability amplitudes of various system of ensemble in various states of phi n. Now, sigma n of a k n t whole square is always equal to 1, and it shows that the probability that a measurement at time t the measurement at time t find of the kth system of the ensemble in a particular state of phi n. Now, time evaluation of density matrix in an ensemble theory. So here now we introduce a density operator rho of t, which is defined by the matrix elements rho mn of t, which is equal to 1 by n sigma k equal to 1 to n akm of t into akn star of t. Now just taken as equation 7. So here actually rho mn of t is the ensemble average of the quantity am of t and an star of t. Now in particular the diagonal element, taking the diagonal element of this density matrix, which is actually rho n of t, and it's my mistake, I wrote here rho mn of t, which is actually rho nn of t. This is actually the ensemble average of the probability a n of t square. That means here rho mn is actually the average of am of t and an star of t. So rho nn of t will be actually the square of a n t and t. So now here we encounter a double averaging process, one due to the probabilistic aspect of the wave function, and next one due to the statistic aspect of ensemble. So in view of this equation, that is equation 6, that is actually a n t of square is equal to 1, we write that rho nn is always sigma and rho nn is equal to 1. That is equation 8, and it's my mistake, I wrote here rho mn of rho mn, it is actually rho nn. Now to determine the motion of a density matrix, so we take the Schrodinger equation of the density matrix, that is IH cross rho dot mn of t, which is actually 1 by n sigma n equal to 1 to k IH cross into a dot km into akn star plus akm into akn star dot. So here the dot is coming from the time derivative of the density matrix. So next line 1 by n sigma k equal to 1 to n sigma LH ml into akn star. So this sigma LH ml akl, that actually came from the derivation we did before, where we took the time derivative of the coefficient ak of m. So that is actually by introducing a quantity L, we write sigma L HML of AKL into AK star n minus the same for the next one AKM into sigma into HNL AK star A k star L. So here HML AKL into AK star n, the first one. So AKL into AK star n is actually the average ensemble average of the quantity, which is actually the density matrix rho Ln. So the next step we get sigma HML into rho Ln of D minus rho ML into HLN. So this is actually the commutator h cap rho cap minus rho cap h cap of Mn. So here which has been made, we have arrived at this conclusion in the view that Hermitian character of an operator h cap, that is h star of Nl, is actually h of Ln. Now using the commutator notation we write that I h cross rho dot is actually equal to commutator h cap rho cap. So from going from the classical equation of motion to its quantum mechanical counterpart, the Poisson bracket rho of h has turned out to be the commutator rho h cap minus h cap rho cap divided by I h cross. Now symmetry. So in any representation of the density matrix other than the energy representation, so the energy representation density matrix may or may not be diagonal. However, it will always be symmetric, that is rho Mn is always equal to rho Nm. Now the physical reason for this symmetry in the density matrix is that in statistical equilibrium, the tendency of a physical system to switch from one state to another state, that is from M to N, will always be balanced by an equal strong tendency to switch between the same states in the reverse direction. So this condition, the physical reason for the symmetry, that is this condition of detailed balancing, is essential for the maintenance of equilibrium distribution within the ensemble. Now the expectation value. So finally we consider the expectation value of a physical quantity G, and this G is represented by an operator G cap given by G, or the expectation value of G is given by 1 by n sigma k equal to 1 to n integral phi of k star G cap phi of psi of k d tau. Sorry, psi of k star G cap psi of k d tau. So in terms of coefficient a k of n, we write the expectation value of G to be 1 by n sigma k equal to 1 to n bracket sigma m comma n a k n star a k m g n m. So where actually g n m is equal to integral psi n star G cap psi m d tau. Now introducing the density matrix rho into this equation, we write the expectation value of G to be summation m comma n rho m n g n m, which is actually equal to summation over n summation over m, sorry, it is actually m rho cap G cap m m, which is actually the trace of rho cap G cap, that is the diagonal elements. And now taking operator G to be I cap, where I cap is the unit operator, trace of rho cap is equal to 1. So but here it should be noted that if the wave functions are not normalized, then the expectation value of G would be given by the formula G is equal to trace of rho cap G cap divided by trace of rho cap. Now at last, the application of density matrix. The first application is quantum chemical one to many body system in this ground state, that is system at absolute zero, and it is shown how density matrix fits into Hartree, Fock and Thom's Fermi schemes. And then a brief discussion is given on the development of theory of diamagnetism. Then a discussion on non-equilibrium process of Kubo's approach to transport theory. And last, the polarization of beams of electrons or photons is discussed and it is indicated how density matrix techniques can be used in the scattering process. Thank you.